just to bring us up to speed, we had talked about, and this is sort of the mechanisms of drug action, how we're going to hang our drugs on the physiology. And we know how we're going to hang them. And the first part we sort of talked about, the drugs are simply going to bind to these receptors for the most part. And that's going to be an affinity process, and we'll talk about that at quite a bit of length. Then we talked about the fact that we've got agonists, antagonists, inverse agonists, partial inverse agonists. And so after they bind, they've got to do something else. And we're going to talk about how we're going to sort of characterize that. And then we're going to talk about a concept called spare receptors, which we haven't introduced at all yet. And when you put all of those together, the ability to bind to the receptor, the ability of the drug to tweak that receptor in some specific way that makes it either an agonist or an antagonist or whatever it's going to be. And then lastly, whether or not there might be spare receptors, you come up with this, some idea of what's the magnitude of that drug effect going to be? How big of an effect is it going to produce? And we're going to try to come away with some explanation for that. The only one that has a really hard and fast, concrete number that you're going to have to get some sense of is the affinity. And that's going to come from this KD value, and we'll talk about that at more length. So that's where we are. We had talked about sort of the theory of drug receptor interactions. And so now we're at this point, we're going to try to quantitate it. And I said there's really going to be three things we're going to quantitate, which will allow us to quantitate the fourth thing. Affinity will be quantitated, and you got to understand what that means. Intrinsic activity will be sort of quantitated on a 1 to 0 to -1 scale. Spare receptors will be quantitated in some ways, kind of thing, we'll talk about it. But the combination of those first three, affinity, intrinsic activity, and spare receptors, will give us some sense of what the actual efficacy of the drug will be. And we'll spend probably 40 minutes on this piece. So this is the slide we had up last. Again, first we got to have a ligand receptor system, and that was all the first handout. That was all about how cells talk to each other. Drugs are going to, for the most part, jump on that system and use it. So we're going to have affinity. We're going to have intrinsic activity. That's the ability of an individual drug molecule, after it binds, to do something to that receptor. Is it going to move it to the active state? Is it going to move it to the inactive state? Is it going to move it to the inactive state really, really well, or only mediocre? So it's a partial agonist kind of a thing. Or is it going to just bind there and not change the active state to inactive state ratio? And that's an antagonist. So that's intrinsic activity. And then receptor reserve or spare receptors we'll talk about. And you add all three of those together, and you come up with what's that drug going to do in terms of the effect. So affinity is the first one. That's the KD. And this is one that sort of maps reasonably well to enzyme kinetics. You've had Michaelis-Menten kinetics and biochem. So essentially KD, a drug has to bind to the receptor in order to produce the effect, if it's a drug-receptor interaction, and that's the kind we're talking about here. KD is what we're going to measure, and essentially that's the dissociation constant. And we'll get into that in a little more detail. But so basically, these are a couple of equations from the text. We're talking about drug binding to the receptor, drug and receptor leading to the drug-receptor complex. And that has, you can map the reaction going toward the formation of the complex and the formation or the separation of those two. Because it's not a covalent bond, they just mass action, they're going to go back and forth and be in equilibrium. The net association is K1 over K2. But really for drugs, we're most interested in net dissociation constant. That's why it's called KD. It's the dissociation net constant. It's KD. It's really the net movement from the drug receptor complex back to the drug and receptor separate entities. KD is the dissociation constant. Why do we care about KD, the dissociation, more than the association? Yeah. Well, we want the drug to be able to unbind so the effect is not constant. That's true also. But really, the net effect of the drug is going to be how many times the drug, not single drug, how many times drug molecules virtually bind to that receptor, let's say it's an agonist. How many times do they bind to the receptor, move it to the active state, and then jump off again after they've done their effect? They have to bind, move to the active state, produce their effect, and then get off because you want another molecule to jump on that receptor and move it to the active state, and then get off. It's the net number of drug receptor interactions over time that's really the magnitude of the drug effect. If the drug binds to the receptor covalently, that receptor is basically unavailable after one burst of interaction. And so you essentially can't get the magnitude of effect. And so KD, the speed at which, or the rate at which it dissociates and makes itself available for more agonist activation, is the most important element. So KD is what we're really going to look at. Yeah, question. You've got a questioning look there too.
Could you argue that KD is also could you argue that it's important for metabolism, or is that in a separate pathway?
Metabolism isn't a word I'd use in here. The molecule will sometimes be metabolized after it's leaving, but that is separate from the association dissociation. Metabolism is a process after it gets further away from the receptor, then maybe it's going to be metabolized, kind of thing. But essentially, it's really the net number of times drug molecules can bind to the receptor, move it to the active state, produce the effect, jump off again, and let more molecules do that. And the most important step after you've done your activation is get the heck off the receptor so another molecule can get on. And that's why KD is really the most relevant term. And that's sort of in here. Affinity is the ability of a drug to bind the receptor. The off rate is more important than the on. So we use the KD, the net off rate, as a way to characterize receptors. And this is a number that everybody in the biomedical sciences will use, and the pharmaceutical sciences will use. We're not going to have really great workable numbers that we look at and see on a regular basis about intrinsic activity. That's harder to measure. There are ways to measure, but it's more nuanced, and it's not something you see in everyday literature. You're not going to see stuff about percentage of spare receptors in a really quantitative kind of way, although both of those two will fit into how a drug's going to produce its effect. But the affinity is a number you're going to see in the literature. So let's talk essentially, how do we get there? So basically, KD is a measure of the affinity of the drug for the receptor, because it's the dissociation, and that's the one we use the most often. But it's also the measure of the concentration that's required to occupy 50% of the receptors. Again, we're trying to quantitate how a drug is going to interact with a particular receptor. And KD is going to be our measure of affinity for that, but it's also going to be, in a mathematical sense, it's going to be that concentration that will occupy 50% of the receptors. And that comes from equation 13.6 here, KD, and you can sort of do the math. I'm going to jump a little bit on this, try to shortcut it, but add a few slides to hopefully make it a little more clear. But KD is basically the free drug, which is D, times the free receptor concentration, which is R, divided by the drug receptor concentration. That's out of the text. You can see where that originally came from if you want. Essentially, when we are at a position, so I said earlier, KD is the concentration at which 50% of the receptors are bound. So if that's the case, if we're in a state where 50% of the receptors are bound, what's the concentration of D, free receptors, to DR, drug receptors that are bound? R free receptors and DR receptors that are bound. That's going to be those are going to be equal numbers. If we're in a situation where 50% of the receptors are bound, the value for R, which is free receptors, will be the same as the value for DR, because half the receptors are bound, and by definition, half the receptors are not bound. It could be a gazillion, it could be 22, or any number in between. But at the KD, if we define it as the point where 50% of the receptors are bound, the number R is going to be equal to the number DR. And so at the KD, the point of 50%, that's going to be the drug concentration. That is, the drug concentration at that point is going to be, by definition, then the KD. I'll walk through a little bit of this. I tried to add some extra slides. So again, D is the free drug. This is a blue background. I don't know if you can tell it's blue. Sorry. Probably should have used another color. D is the free drug. R is the receptors not bound. DR are the receptors bound. And so when 50% of the receptors are bound, when DR and R are the same, they'll cancel out, and the KD is actually that drug concentration. So the concentration at which 50% of the receptors are bound is the KD. The drug concentration when 50% of the receptors are bound. Any other numbers you plug in there, and you won't get that exact example. You get the full range of concentration versus binding. This is actually from the next chapter, but I thought I'd throw it in and try to give you some sense of it. This is the enzyme kinetic stuff, Michaelis-Menten stuff. You've probably seen this before. Substrate versus Vmax of enzyme activity, and you have a Km, which is the concentration at which you get a half maximal effect. That substrate concentration that gives you your half maximal enzyme activity. By parallel, and again, this is from the next chapter, but I stole it. I relabeled it a little bit. If you have the drug concentration now here on the x-axis, instead of the substrate, this is a drug, and now this is a receptor, and you have the fraction of receptors occupied going up to all of them, 100% is a fraction of 1. KD is that concentration for that drug and that receptor that occupies 50% of the receptors. It's very, very comparable to Km in Michaelis-Menten kinetics. That is the very, very commonly used value to quantitate drug receptor interactions. It's relatively easy to obtain in a classic kind of a receptor binding assay. It is valid for a lot of kinds of comparisons, and so it provides a quantitative kind of piece of information about the affinity of that drug for that receptor. It is very specific for a particular drug and a particular receptor. For example, we have a drug, we've got a natural ligand, norepinephrine. Norepinephrine can bind to alpha receptors. It can bind to beta receptors. Within the alpha group, there's alpha 1 and alpha 2. Within the beta group, there's beta 1, beta 2, and beta 3. It does not have equal affinity for all of those receptors, but when norepinephrine in me binds to my beta 1 receptor in my SA node, it has an affinity comparable to your norepinephrine binding to your beta 1 receptor in your SA node. It is consistent across individuals, but it's unique to that particular receptor. So the norepinephrine binding to the alpha receptor may not have the same affinity, because it reflects essentially how well does the norepinephrine molecule park on that receptor surface. Yeah, question.
So if you want a lower KD to have higher affinity to the drug, wouldn't having a low KD also be like a disadvantage because it would stay in the complex longer when this is associated?
A low KD is not necessarily a drug that dissociates slowly. But typically you want a low KD because that's a drug that has what we refer to as higher potency. If it has, and so we'll get a little bit into that next week, next week when we talk about it. But basically, the lower the KD value, the more affinity for that receptor. If it has a super high KD value, it means you've got to give a lot of the drug in order to the person in order to occupy that receptor. There are probably some other receptors that are being occupied by that drug too. And then you lose what's called selectivity. This is just an example, and this is out of antidepressant literature, but these are a bunch of antidepressants, and if you're in a pharmaceutical company and you're trying to build a new antidepressant, what you probably do, at least you did up to about 10 years ago, is you had a whole array of receptors and transporter molecules and potential sites of action, and you just made a new drug and you laid it out against those receptors and said, what's the KD? For what's the affinity of that drug for those various receptors? And that would give you some potential information about possible use. And again, KD is a hard and fast value that is sort of universally accepted as the way to measure the affinity of the drug for the receptor. It's out there, you'll see it a lot. Drugs with a low KD tend to be the ones that we want to use because, especially if the KD for the receptor of interest is much lower than the receptor for some other side effect that we might not be interested in. So it's a way to also, looking at relative KD values, we get a sense of what the selectivity of the drug might actually be too. Again, so KD is the concentration that binds to half the receptors. The affinity for the receptor tells us nothing, though, about the action of the drug at that receptor. So the point of affinity is simply to quantitate how effectively this drug binds to this receptor. But it doesn't tell us whether it's an agonist or an antagonist or an inverse agonist. It just says it binds. Agonists, antagonists, inverse agonists all have affinity. They'll all bind to the receptor. And that's sort of the basis of what's called occupation theory. But occupation theory sort of falls down because it doesn't allow us to say, well, when this drug binds, it does this, and when this drug binds, it does the opposite thing. When this drug binds, it doesn't do anything to the receptor. That requires more than simply occupation. We have to have that to go to the next step, but the next step is looking at the actual intrinsic activity of the compound. So again, this is occupation and KD. So occupation theory is based on this affinity thing. According to occupation theory, we're going to get a 50% response when 50% of the receptors are occupied. You're going to get a 100% response when you occupy all the receptors. But there's a problem, and I said this before. The problem is it won't differentiate between an agonist and an antagonist because they both will bind to the receptor. And occupation theory says they're not different. If the KD is 10 nanomolar between an agonist and antagonist, simply looking at affinity won't tell you how they're different. They could both have a KD of 10 nanomolar, or micromolar, whatever it would be. The other thing that occupation theory doesn't do, and we'll come back to this a little bit more too, we haven't, this sort of a newer concept, is that occupation of the receptor doesn't tell the whole story if there are what are called spare receptors. And that is an awful term. And we'll get to it, and I'll tell you why it's an awful term, because it's an adjective for the noun receptor, and it shouldn't, that's not what's different in the system. It's not receptors that are different. It's something that's beyond the receptor that's different, but they call them spare receptors. And we'll get to that. So in order to understand really what a drug's going to do at the receptor, you start with the affinity, which is quantified with this KD. KD is the point where 50% of the receptors are occupied by the drug, that concentration of the drug that occupies 50%. But then you have to add intrinsic activity and considerations of spare receptors. So we'll do those now. So intrinsic activity, and this one we've already foreshadowed, and we've talked about this already. Intrinsic activity is essentially the drug will exert an effect on the receptor to mimic the endogenous ligand to change the portion of receptors that are in the DR state. That is, if it's a full agonist, after it binds, it converts all the receptors to the DR plus state, the DR with an asterisk state, the activated state. But intrinsic activity is going to vary from full agonists, like I said, all the receptors move to the active state, to full inverse agonists, where all the receptors go move to the inactive state, or they can be antagonists, which bind and don't change the conformation ratio. They can be partial agonists and partial inverse agonists. That we're going to get with the term intrinsic activity. And so for that, we don't really have a concentration measurement is effective. It's not as easy to measure, and it's not as universally applied as KD, the measure of affinity, but there is an arbitrary system the arbitrary scale is put into place. If you're looking at a single receptor and a single drug molecule, after it binds, if it converts that receptor, or if it converts all the receptors to the active state, that is a full agonist that has an intrinsic activity of 1. We've already talked about what a full agonist is, and now we're saying that if a compound is a full agonist at that receptor, it will have an intrinsic activity of 1. If it's a full inverse agonist, if it binds to the receptor, moves all of them to the non-active conformation, that's a full inverse agonist. That will have an intrinsic activity of -1. So you got the max and the min already laid out there. If it's a full competitive antagonist, we said, what does that do? It binds to the receptor. It doesn't do anything to the ratio of active and inactive conformations. It just binds and occupies. But it also will then prevent the endogenous ligand or some other drug from binding. But it binds and doesn't change the ratio. That will have an intrinsic activity of 0 because it doesn't change the conformation percentage. Partial agonists will be between 0 and 1 because they do some change in the direction of the active conformation, so they're going to be greater than 0, but they're not as big as a full agonist, so they have somewhere in between 0 and 1. And partial inverse agonists, by analogy, will produce a response that's less than the full inverse agonist, but bigger than the antagonist, so their intrinsic activity score will be between 0 and -1. I've already shown you this picture, and this just shows you what's going on, and it sort of puts it in the context of those two equations. But a full agonist on the top moves everything to the active site. That's an intrinsic activity of 1.0. Full inverse agonist moves everything to the inactive site. That's an intrinsic activity of -1. Antagonists have intrinsic activity of 0, and so on and so forth. This is actually a little, we'll jump ahead a little bit because I think this is a good time to put this in. This is a dose response curve for what it looks like with a full agonist, a partial agonist, and an even weaker partial agonist. I didn't draw the antagonist, but this is activation of the receptor on the y-axis. And this is a dose. I did this with Excel. I had log numbers, and it created unlogs when it made my plot, so it should be a log scale. My apologies. Not 1, 2, 3, 4, 5, 6. Maybe 1, 2, 4, 8, 16, something like that. But anyway, if it's a full agonist, when you occupy the receptors and you give higher and higher doses, you get a maximum response, which is going to be 100%. If the drug is a partial agonist, and I'll say one caveat because we're going to talk about this in a little bit. This doesn't involve any spare receptors. No spare receptors in this analogy. We'll talk about spare receptors and how they gum up the works a little bit, make the interpretation more complicated soon. But in the absence of any spare receptors, if you have a drug that has affinity for the receptor, but it has efficacy of 1, you'll get a maximum response that's at 100% here. If it is a partial agonist, maybe it's got an intrinsic activity of 0.5, you'll get a dose-related increase, but it'll stop at some level well below the 100%. In this case, the example, it stops at 50%. If it's an even weaker partial agonist, and this has got an intrinsic activity of 0.5, the one that's sort of greenish gold, you get a very, very weak effect, almost no effect. And that's the illustration of what a full agonist, a partial agonist, and an even weaker partial agonist would do in terms of effect when there are no spare receptors. We'll get to spares in a second. If it were an antagonist, you'd have a dose-response curve that was at 0 the whole time. And an inverse agonist would go the other way kind of thing. But this is just one picture. I'll give you one more example out of the real world. This is the benzodiazepine GABA receptor complex I talked about before. Benzodiazepines are modulators of this GABA A site, which is controlling the chloride channel. Within this benzodiazepine site, it is a receptor in its own right, even though it's an allosteric modulator. It is a receptor that serves as an allosteric modulator of the GABA A receptor. But within this receptor, we have an antagonist, we have full agonists, we sort of have an experimental work. We've got full inverse agonists, we've got weak inverse, partial inverse agonists, and partial agonists. So if what's going on here, when you give a benzodiazepine, I'll try to explain the next slide. What's going on here is when you give a benzodiazepine, there is normally GABA activating this GABA A receptor. That's always happening, and it's letting in some degree of chloride ion influx. If you activate the benzodiazepine receptor with an agonist, you enhance that chloride channel opening. You enhance that chloride channel opening. If you have an inverse agonist at that benzodiazepine receptor, you will actually reverse that chloride channel opening. And we have a full range of agonist efficacies with the benzodiazepine drugs. This is an ugly slide, I apologize. It's out of an old review. The drugs that we use, the benzodiazepines we know and love, diazepam, flurazepam, midazolam, I can't even read some of these, clonazepam, these are all full agonists. What they do is they facilitate the effects of GABA to activate the GABA A receptor and open the chloride channel. And what this is the modulation of GABA-stimulated chloride release, chloride influx. So movement to the top is what you would expect a positive modulator to do. Benzodiazepines facilitate GABA effects. There's a benzodiazepine antagonist compound, flumazanil, which is called romazicon and RO15 1788 if you're hot from the Roche. But flumazanil is an antagonist. It will not change that chloride channel influx that's mediated by GABA because all it does is it blocks the benzodiazepine receptor. There are inverse agonist compounds. These are experimental compounds that actually will undo the GABA-mediated opening of the chloride channel. And they're inverse agonists. These have intrinsic activity of -1 down here. Intrinsic activity of +1 out here at diazepam, -1 at the other end. Intrinsic activity of 0 for flumazanil. And we have partial inverse agonists here in the middle and partial agonists here in the middle with the benzodiazepine receptor. So there are examples of this. This is sort of most of the drugs we use in medicine today are either full agonists or we have the antagonists, but there's potential for inverse agonists and partial inverse agonists as well. The idea is that this is intrinsic activity. All of these drugs have affinity for the receptor. They will all bind to that benzodiazepine receptor. Their affinity values are not going to be equal, but for each drug there is a concentration at which you'll get 50% occupation of that benzodiazepine receptor. What happens after that is the intrinsic activity part, and you have drugs that go from fully undoing what GABA is trying to accomplish to fully amplifying what GABA is trying to accomplish to having no influence. And that's this range of intrinsic activity. Questions on that intrinsic activity concept. So we're gonna bind to the receptor, and then after we bind, and that's going to be our KD, and that's a nice value. Everybody loves that. We can report that in the literature. And when you see a low KD, you're supposed to say, oh, I think that means it's going to have pretty strong affinity for the receptor. Maybe some selectivity will come from that. Next is the intrinsic activity, which is not so widely reported in the literature because it's harder to study. Got a question? So her question was, what do I mean by +1 for intrinsic activity for the agonist? It's an arbitrary scale. The best you can do is +1. That is, intrinsic activity of +1 means that after that drug binds that receptor, it produces the biggest possible effect you can get at that receptor. And that is given a value of +1. And conversely, if it's an inverse agonist, after it binds that receptor, it moves all those receptors to that inactive conformation and undoes everything that that receptor can do at its maximal effect, and that's a -1. And if it's neutral, it's a 0, it's an antagonist. But I think your question hits on the very point. KD has a value that's sort of real and real world and is measurable. Intrinsic activity is on an arbitrary scale from 0 to 1 on the plus side, from 0 to -1 for the inverse agonist side. And that's just, that's sort of, it's arbitrary. It's not used as often, it's not measured as easily. But it is an important component of what a drug's going to do. Because first the drug binds, and we can measure that nice and cute with the KD, but then we have to say, what's the drug going to do after it binds? And that's the intrinsic activity. We're comfortable with that? Okay, we'll move to the third part, which is receptor reserve, and all three of these together are going to tell us something about what we call the efficacy of the drug. But receptor reserve, which is also called spare receptors, awful term. This is not what we're talking about. So this is a spare tire. You got a regular tire and a spare tire. And we know what a spare tire is. A spare tire is the tire that even before they had these rinky-dink little tires, when I started driving, spare tires were still tires that you didn't really like. Spare tire was barely a tire that sort of held air, and you could drive someplace with it, but you really didn't want to stay on that tire forever. It was a tire of a different sort. A spare tire in today's car is clearly a tire of a different sort. No further than 50 miles an hour. I don't think that's the standard for most tires. But they call them spare receptors, and people think, oh, well, they're like extra. They're sort of a backup. They're sort of out there in case you need them, in a case of an emergency. That's not the way to think of spare receptors. So for cars, spare tires are not normal. There is no such thing as a true spare receptor. Oh, we got a bunch of good beta receptors. I'm a spare in case they need me, in case one had to blow out. Maybe they can finish and get all the way home on their jog because they need another beta receptor. No, that's not it at all. They're not spare receptors. What is really different about the system is that some systems run out of signal transduction molecules and pathway after you reach a certain level of activation. So remember, we said, for example, norepinephrine, activating a beta-1 receptor in the SA node of the heart. That beta receptor is a G protein coupled receptor, makes the GTP alpha thing, that splits off and goes over to adenylate cyclase, and it makes the cyclic AMP. Well, if that system is lacking and runs out basically, you can continue to activate the beta receptor, but if there's no capacity to stimulate adenylate cyclase anymore, what good is it? That's extraneous above any useful level of beta receptor activation. So theoretically, and it's not just GPCRs, this could happen in a lot of different kinds of receptors, but you can activate a receptor, you can, I should say, bind a receptor, have affinity for it, you can have efficacy to try to drive that receptor, but if the signal transduction system is done, what's going to happen is you're not going to get any more bang for additional receptor occupation and activation. Now, when this term was sort of developed, people said those are spare receptors. Well, the reality, it's not the receptor probably that's sort of changing. What really is changing is the transduction mechanism is running out of gas. So that's why I say spare receptors is a misnomer. It's an adjective modifying the wrong thing. The receptors are just ordinary receptors. But what happens in some instances is that you can get a maximal effect without activating all the receptors, because your maximal effect is going to be determined by ultimately how much signal transduction you can generate. So remember, bind the receptor, that's affinity. Activate the receptor, if it's an agonist, a full agonist, that's your intrinsic activity. If you do that to a point where you've used up all your signal transduction, more ligand can bind to the receptor and can try to activate the receptor, but it's not going to have a consequence inside the cell. And again, that's called spare receptors, which is not the right way to describe it. A receptor reserve would probably be more accurately described as some kind of limitation downstream from the receptors, maybe like you're maxing out the signal transduction process. Now, there's not good quantitation on a lot of this. So this is sort of in hypothetical kind of stuff and at one level. Yeah, question?
Spare receptors, do they not have an effect since you've already reached your maximum?
You use the word spare receptors, I'll let you do that. But yeah, that was his question is, so activation of spare receptors doesn't have an effect because you've already used your maximum transduction mechanisms. Exactly. But they're not really spare receptors in the sense that, well, they're there in case you need them and they're different from other. They're ordinary receptors. It's just in some situations, you only need to activate fully maybe 10% or 50% of the receptors in order to get the maximum response. Those remaining receptors are identified as spare, although what's really, the description would be limitations in the intracellular surface or in the rest of the transduction process. Yeah, question?
Here you are talking about a receptor, you're not talking about a catalyst? I thought it was just
I'm not talking about, there are specific examples I'm not going to give you. I mean, there are some specific examples, but we're not going to bore you with those. It's really the concept that we know they exist in some situations. So what we're trying to get at, again, we're trying to get from a drug out there in your body to an effect. And first we say it has to have affinity for the receptor. And that we can quantify, no arguments about it, that's your KD value. That's your concentration of the drug required to occupy half of the receptors. Now we also have to consider the fact that some drugs will activate the receptor, move it to the active form conformation. Some drugs may, and those are full agonists. Some drugs may move it to the inactive conformation. Those are full inverse agonists. Some may not change the conformation, although they bind. Those are the antagonists. We got the partials. That's another factor to consider when we think about what's the drug going to do for you. And the third thing is, maybe that receptor system has what are called, inappropriately called, spares. And so in some situations, you can get a maximum effect by only occupying 50% of the receptors, for example. And those extra receptors don't matter much. But here's the question, because they do matter in some situations. Where's the situation where having an additional 50% of receptors, let's say we've got a system that has 50% of what they'd call spare receptors. And in the case of a full agonist, those 50% of those receptors are wasted because once you get beyond the full signal transduction by activating half of those receptors, you don't need the rest of them. But where's the situation where you could get a bigger bang if you had spare receptors?
Have like a competitive inhibitor or something like inverse.
If you have a competitive inhibitor, or the classic example is a partial agonist. Let's do just one drug at a time. We could combine drugs and we'll get there too. But the classic example is if you have a partial agonist, let's say there's a drug that has intrinsic activity of 0.5. It's a partial agonist. It can only convert about half the receptors to the active state. But if there are twice as many receptors as would be necessary for a full agonist, that partial agonist can bind all of them and activate all of them at a half level, and that will get you a bigger bang. So in the case of spare receptors, a partial agonist, a drug that has an intrinsic activity of less than 1, let's say it's 0.5, can in some situations give you as big an effect as a full agonist. It's not because it has a different intrinsic activity. It's not because its intrinsic activity has changed. The partial agonist for each receptor interaction will produce about half maximum effect. But if it has twice as many receptors that it can bind to because they're so-called spares, now you can get that full effect with a partial agonist. That make sense? Simpler than yours. We'll get to yours on Monday when we do combination kinds of things. But the point is, they're called spare receptors. They're not different, though. They're not less than normal receptors. They're not the ones that you sort of wait till the very end kind of thing. They're just out there. It really would be better described as sort of a limitation at some point after the receptor. Let's see, I think we had just walked through this situation. Sometimes the number of receptors occupied doesn't determine the maximal effect. Sometimes there are some additional receptors, and when you have a partial agonist in the presence of these so-called spare receptors, you can get a bigger effect of the partial agonist. Again, I'd call it receptor, I wouldn't call it receptor, a spare receptor, you might call it receptor excess, because it's more receptors than is needed for a full agonist. Question? Yes, yeah, the big thing that happens in the case of spare receptors is all of a sudden a partial agonist can give you a bigger maximal effect. A partial agonist can approximate or even reach the maximal effect of a full agonist if they're what they call spare receptors, or if you want to call it a receptor excess, that kind of a thing. Full agonist, once it's occupied, if it's 50% spares, once it's occupied 50% of the receptors, you can occupy another 20% and you're not going to get a bigger effect, because that's not limiting the response. The response is being limited below the receptor. So we call that receptor reserve. Somewhere there's a good graph of this, but essentially we'll get to this in a second. So we get receptor reserve is the spare receptors. So three things we've talked about. The first two are really drug receptor specific kind of properties. Affinity, and we're going to measure that. We're going to give you a KD, it'll be so many micromolar, and we're going to compare all kinds of drugs with KDs for the same receptor. We're going to look at the same drug at KDs at different receptors to show selectivity of the drug, potential value there. That's a really hands-on kind of a number. Intrinsic activity, arbitrary scale from 1 for a full agonist, 0 to an antagonist, -1 to a full inverse agonist. That's going to impact what the drug does as well. And lastly, receptor reserve. In the case of receptor reserve, or excess receptors, or whatever you're going to call it, something that has intrinsic activity less than 1 can enhance its intrinsic activity if there are more receptors available, if there are spare receptors available. And so all those are going to come together for efficacy. Efficacy is simply the effect that you get when you give that drug. It's dependent upon affinity, which is binding to the receptor. It's dependent on intrinsic activity, which is the ability to activate or turn off, or just simply bind in a neutral way that receptor. It's related to whether or not there are spare receptors in that system. Intrinsic activity is a unique drug-receptor interaction. Each drug will have an intrinsic activity for that within that receptor when it binds. Affinity is a drug-receptor specific kind of a thing. Spare receptors has got nothing to do with a particular drug. That's a physiology issue. But the outcome is different if there are spare receptors versus not spare receptors when the intrinsic activity is less than 1. So the affinity, intrinsic activity, and efficacy are all going to come together here. The efficacy of an agonist is a measure of how efficiently it stimulates the receptor to produce the effect. An agonist is a higher efficacy when it produces a bigger effect, and lower efficacy when it produces a smaller effect, obviously. How are we doing for time? So I've sort of touched on the spare receptors. This comes back to the spare receptors. Let's consider that we've got 4 drugs, and this is a picture out of Goodman and Gelman. I tried to soften the text a little bit and clarify it a little bit. But let's say drugs A, B, and C all work at the same receptor, A, B, C, and D. They have different degrees of intrinsic activity, and they can all produce the same maximal effect. So this will be a system with some spare receptors. Let's say the number of filled circles represents the number of receptors you need to occupy by that drug to get the effect. So drug A has to occupy all 10 receptors to get the maximum effect. On the other hand, drug D, even though there are 10 receptors there, only has to occupy 1 receptor to get that maximum effect. Why? Because it has higher intrinsic activity. D has higher intrinsic activity than A. B and A are about the same. They both have to occupy and activate all 10 receptors. C is sort of in the middle. It has to occupy 50% of the receptors, but 50% can be unoccupied and you'll still get the maximum effect. So in terms of intrinsic activity, D is going to be given the value of 1. It's the highest. C will be given a value of, I don't know, point, whatever it is. If 50% spare receptors, it'll be 0.2 probably. And A and B will have even lower intrinsic activity. Yeah, question?
What about the KD for those drugs?
The KD can be varied across those drugs. It does not have to be the same. Because KD isn't going to be related to, once you bind, they have to have a KD value that's reasonable. Let's put it that way. They have to be able to bind for this analogy to work. But they don't all have to have the same KD. They don't have to have a KD that's within, 1 log unit of each other and those kinds of things.
So it doesn't mean that KD of the drug D is higher or lower?
This has nothing to do with the ability. This has nothing to do with the ability to bind to the receptor, except that they all have to bind to the receptor. But it doesn't say you have to bind really avidly, have a low KD, or have a high KD. You just have to be able to bind to that receptor. Drug D has really high intrinsic activity. We'll give it a 1. C is intermediate, and A and B are even less than that. But they can all produce the same effect if you're measuring some outward effect. Why? Because there are a whole lot of receptors that would be called spares. So A and B must activate all the receptors to get the maximum effect. There are no spare receptors in this example. But you can still get the maximum effect with this drug because there are that many receptors out there. Drug A may not have it's not going to have the intrinsic activity of C or D, but it can still, in the end, when you net it out, it activates, it binds and activates more receptors, although each receptor is activated at a lower level. The mathematical product of that is essentially still going to be the big effect. Drug C can get the maximum effect with only 50% receptors occupied. So there's 50% spare receptors for drug C and 90% spare receptors for drug D, because it can get the maximum effect and a whole bunch of receptors sitting out there saying, what about me, what about me? And they're not needed. Question?
Max effect is when we've used all the second messengers.
Yeah, well, in this, and that's one way that you'd have that maximum effect, yeah. Yeah.
Mr. Gates, that drug D is going to be the full agonist, drug C partial agonist?
Yes, you're exactly right. So her question was, so drug D is a full agonist with intrinsic activity of 1, we'll say. Drug C is going to be a partial agonist with lower intrinsic activity. Drugs A and B, even lower intrinsic activity than C. So we're going to give them some scores there. Yet they can all produce the same maximum effect. Why is that? And this is the picture you're going to get. And this is why spare receptors can be important. So this is essentially the left half. I've already shown you this. This is the effect that you can get with a drug with a full agonist, the blue line, intrinsic activity of 1, partial agonist, intrinsic activity of 0.5, weak partial agonist, intrinsic activity of 0.1. If there are no spare receptors, obviously you get a bigger effect with the blue line than with the red or the green. On the other hand, if you have spare receptors, in the example we showed you, with drug C, you can actually get a full response, full maximum response with that drug, even though it's a partial agonist. And you can get a bigger response with drug A, although it doesn't go to the max in this case, with spare receptors. And this is the 50% example, this is not a 90% spare example. Yeah?
So spare receptors are really only a factor for agonists, not inverse agonists?
Spare receptors will be, the question was, is this only agonist and not inverse agonist? Spare receptors are going to come into play for both agonists and inverse agonists. I didn't show you the inverse, but that can be also come into play there. The real issue is that spare receptors come into play only with partials, whether it's a partial agonist or a partial inverse agonist. If it's a full agonist, you don't get a very dramatic difference between a situation with spare receptors and not spare receptors. They have the same maximum response.
So like if you had like a full inverse agonist, though, wouldn't there still be receptors available for an agonist to bind to get the response?
Oh, you're talking about two drugs competing for each other. Well, we can get into that too. His question was, if you have a full inverse agonist and you only need to occupy 10% of the receptors, can an agonist bind those other 90% or a partial agonist? And that's going to make the story complicated. Yes, drug-drug interactions, that can happen. But to keep it simple on this analogy, if a full inverse agonist, it will produce a maximum anti-drug effect, if you will, with a smaller percentage of the receptors. And so if you have a partial inverse agonist, theoretically you can get a maximum effect because you can occupy those additional receptors and push that effect bigger. The point here is, again, we're trying to say what's going to determine the effect of the drug. We got one thing that we can all agree on, very quantifiable, very cool, KD. The drug binds to the receptor, we measure the affinity as a KD. Low KD values mean higher affinity. KD is defined as the concentration that binds half the receptors. That we're cool on. The stuff that's a little more fuzzy is the stuff that comes into play when you're trying to determine the effect of the drug, and that is, what's the actual intrinsic activity, and we use an arbitrary scale, full agonist 1, full inverse agonist -1, antagonist 0, things in the middle, and then we look at the potential for spare receptors. We're not, in most cases, in most cases that you're going to run into, there's not going to be a quantitation of how many spare receptors there are, and so this partial agonist will produce this effect relative to this full agonist kind of thing. But you will see that come into play on occasion, but it's less quantifiable. The quantifiable piece is the affinity of the drug for the receptor, KD. But the other two will come into play when you're looking at what does the drug actually do. So we've got all four of these. All three come together to give you the efficacy. You've got to bind, and that's your KD, that's your affinity. Affinity, KD, is the concentration where you bind half of the receptors. After you bind, you got to do something, or not. If you're an antagonist, you don't do anything, you just bind. But if you're a full agonist, you're +1. If you're a full inverse agonist, you're -1. If you're partial, you're in the middle. So that is a part of what's going to end up leading to your ultimate effect. Another part of that is there receptor reserve, and what's the magnitude of that receptor reserve? And that will come into play as well. And all of those will lead to essentially the post-receptor response. What is this drug going to do? And it's going to do it because A, it binds, 2, it does something after it binds, and 3, maybe there are spare receptors. So that's quantitation. Now we'll talk about antagonism. We'll talk about competitive antagonists, non-competitive functional and chemical antagonists. Competitive antagonists, a lot of the drugs are competitive antagonists. Propranolol is a competitive antagonist for beta receptors. Essentially, they have affinity for and they bind the receptor as the same receptor as the natural ligand. They bind both the active and the inactive state. They don't change the balance. So they have an intrinsic activity of 0 if they're an antagonist. The antagonist and the agonist, they'll compete for each other for the same receptor. And the antagonist won't, even if it doesn't have any intrinsic activity, if it has an intrinsic activity of 0, it doesn't change the normal active versus inactive conformation. Very often the antagonist will reverse the effect of the endogenous ligand because it will block that. And so it will get an effect that's the opposite of the endogenous ligand. So propranolol is an antagonist at the beta-1 receptor in the SA node. It's not going to change the relative conformation of active and inactive beta receptors on my SA node, but because I have norepinephrine always from the sympathetic nervous system activating that beta receptor, giving me a big part of my heart rate, propranolol will block that effect, and you'll get a bradycardic response. You'll get a slowing of the heart. Not because propranolol does anything directly to the receptor, but rather because it blocks the intrinsic ligand from doing its thing. A lot of receptor antagonists are used in that context. This is a picture of it. It's a bad picture. I think you've sort of got the idea. This is a graph. Again, we do dose responses in the next chapter, but I thought I'd slip in a couple. So this is what a competitive antagonist looks like in the presence, let me put it this way. This is what an agonist does, a full agonist does in the presence of a competitive antagonist. The blue line is the agonist alone, and we haven't talked about it, but this is dose. It should be a log scale. Again, I used Excel. Probably should have changed that. But anyway, as you do dose increases with an agonist, you will get an increase in the response to some maximum of 100%. If that same agonist now is examined in the presence of a low dose or a little bit of the antagonist, you'll still get a dose response curve with that agonist, but it will be shifted to the right. That's because the competitive antagonist is just a competitive antagonist. That is, it's not covalently binding, it's just a mass action kind of an interaction. The more agonist you give allows you to overcome that competitive antagonist. The phrase that some texts use is surmountable. And so with a competitive antagonist, you'll very often get a parallel shift to the right in the dose response curve. Previously, I could get, and these are bad numbers because it's not a log scale, but I get about a 50% response with 3 as my dose. In the presence of a low antagonist, I have to give 4. I have to give a higher concentration of my agonist to get a 50% response. And that's just a competitive antagonist. It's a lot like a Michaelis-Menten kinetics kind of thing. If you give a higher concentration of the antagonist, you'll shift it even further. But it is still surmountable. That is to say, you can still achieve the effect of the drug if you give higher and higher concentrations of the agonist. This is the agonist concentration on the x-axis, response on the right axis. Blue is without any antagonist. Red is with a little bit of the antagonist. Green gold is with an even higher concentration of the antagonist. Competitive antagonists will produce a parallel shift in the dose response curve to an agonist, and it will be surmountable. They'll have the same maximal effect because they still can get up to 100%. You just have to give a higher dose. So that's competitive antagonists, and we'll go through that. We'll see those a lot more in the next chapter. Non-competitive antagonists, they don't interact with the agonist for the same binding site. There's an allosteric kind of antagonism or downstream kind of antagonism. Allosteric antagonism is essentially where you, by working at an allosteric site, you change the agonist, you change the ligand-receptor interaction to reduce the effectiveness of the ligand-receptor binding so that you can reduce the effect of the drug. An example from what we talked about, benzodiazepines are allosteric facilitators of GABA neurotransmission, GABA-A neurotransmission. That's how they work. The benzodiazepine inverse agonists, if they were used in humans, do just the opposite. They undo. From an allosteric perspective, they reduce GABA-A neurotransmission. You can have downstream antagonism. And downstream antagonism is a situation where you have a series of events that's happening. If something early in the pathway is happening, but it's dependent upon a later part of the pathway, if you block the later part of the pathway, you're going to block the effect. In the beta receptor, for example, we said, okay, let's say I walk out of the building and I'm just about to cross over the parking lot and there's a big truck coming at me. I have this huge excitation and I get this adrenal release of norepinephrine and epinephrine that prepares me for some flight-fight reaction so I can get away and run away from the truck. That's a part of that is an excess of epinephrine and norepinephrine acting on the beta receptor, beta-1 receptor in the SA node of my heart that says, speed up, heart, because you're going to have to do some work pretty soon. And that works by then working through G protein coupled receptors, which then changes cyclic AMP and all those kinds of things. If something is blocking that downstream pathway. If I prevent GTP from binding to the alpha subunit and swimming over to the adenylate cyclase, I'm going to effectively block that sympathetic induced tachycardia. But I'm not going to do it by blocking the beta receptor. The beta receptor is still clean and good. I get an adrenal release. I get way activated. I have a whole lot of norepinephrine activating my beta-1 receptor. But if that doesn't end up going all the way through the system, that is to activate cyclic AMP, I'm not going to get a response. That's an example of a downstream kind of an antagonism. The text, I think, uses a muscarinic receptor. I'm not sure. It uses an alpha agonist. But we were talking about beta agonist, but basically it's the same concept. If the drug is working at the receptor here and you're interfering with the signal transduction process here, you're going to block the drug effect. But it's not because of a direct interaction of your antagonist working at that receptor. It's working at a downstream site. There are functional antagonists. As I said before, in the heart, my normal sinus rhythm is really controlled by two things that are always in competition with each other. There's a certain part of my sympathetic nervous system that's releasing norepinephrine to act on beta receptors that says, go, 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 have a rapid heart rate. At the same time, my parasympathetic nervous system, which is acetylcholine, working at muscarinic receptors, and don't worry about the details, but my parasympathetic system also is acting on, in this case, muscarinic receptors on the SA node that says slow, slow, slow the heart down. And they are constantly battling each other. And essentially, if I do something that increases my sympathetic tone, it wins the battle slightly over the parasympathetic tone. On the other hand, if I eat a big meal and I sit down to take a nap, my parasympathetic tone says, hey, you just ate a big meal, we got to do some digestion, let's sort of worry about the flight and flight stuff later, sit down and sort of rest a little bit. My heart rate will go down as I spend more of my time and energy on digestion. That's sort of an example of sort of a functional antagonism. Another example that the text likes is like stimulants and depressants. The idea that, that sort of suggests that if you're drunk and you drink a lot of coffee, you're going to sober up. And we know that doesn't work. But at one level, you sort of are a wide awake drunk. So I guess it sort of works at some level. But that's an example of sort of a functional antagonist. Something that clearly cocaine and alcohol are not working at the same initial sites, but or caffeine and alcohol, let's be more legal, I guess. But if you're drunk with alcohol and you drink a lot of caffeine, you're going to be a little more alert than if you didn't take the caffeine. It's not as if you're completely sobered up, though. And then there are chemical antagonists as well. These are things that might actually complex with the drug that keep it from getting to the receptor. Sometimes we can use chelating agents to and in the case of toxicology, for example, sometimes something has been ingested and you want to prevent it from getting to the receptor, you can use some kind of a drug that'll bind it and chelate it and take it out of the system. Or probably maybe not exactly a perfect example, but if someone is overdosed on something orally, at some point you can give them activated charcoal and that can bind that and prevent it from being absorbed. That's a chemical antagonist of sorts. How are we doing for time? 9:29. Okay, we'll finish this handout, but we probably won't go to the next one because, A, it's not posted on Blackboard yet. Stereoselectivity. I've already talked about stereoselectivity. Drug receptor interactions exhibit stereoselectivity, but that doesn't mean that only one isomer is going to bind to the receptor. Because there are a whole lot of receptors. In some cases, there are multiple receptors out there. One isomer might bind to this receptor with some degree of affinity and produce an effect, and the other isomer might fit with this other receptor. So stereoselectivity does not mean only one of the isomers is active, but it will mean that one of the isomers will be preferentially active at a particular receptor. But then you have to consider all the other possibilities. And these are just some of the possibilities. For example, for barbiturates and warfarin, one isomer will be active and the other will be inactive. That's pretty straightforward. There's an active and an inactive isomer in that situation. For NSAIDs, one isomer is active, and the other would be inactive also. In another example, one enantiomer would be active, the other enantiomer might be an antagonist at that same receptor or at a different receptor. Or you get some combination where one has good effects, beta blockers, the L isomer is active, and the R isomer is hypolipidemic. Maybe you can get a double whammy out of it. The R isomer is not a very good beta blocker, but it may have interactions on another receptor. What I'm trying to say is that you don't just simply say, well, in life, the R isomer is the one that's going to bind to the receptor. There is stereoselectivity, but it varies across drugs, and it varies across receptors. So that's the stereoselectivity point. It is not the case that, again, it is the case that there's a stereoselectivity to binding to a particular receptor. It's got to have the right three-dimensional conformation to fit. But the other isomer might fit in another receptor pretty well, actually. Interactions with enzymes, we're not going to talk much about that. Dr. Stemler is coming in, I guess, in about a week or so. He'll spend quite a bit of time talking about that. So the actual drug interactions with enzymes, we won't talk about. And then the last thing we want to talk about is what are called non-receptor-based actions. So we talked a lot about drug-receptor interactions. There's sort of this normal ligand-receptor physiology that we talked about in the first lecture. Now the drugs are going to jump on that receptor system, and then maybe they'll be agonists, inverse agonists, partials, antagonists, but they'll work within that system. Maybe they'll be allosteric modulators, those kind of things. But there are also drugs that produce effects that don't really work through receptors. So some drugs work extracellularly, some work intracellularly, but some work at just sort of things out there in the body that are just out there. And acids and laxatives and cathartics really don't have specific receptors per se. Other drugs may work at cellular sites and membranes, but they're primarily the result of their physical chemical properties rather than any interaction with the receptor. A classic there is what's called an osmotic diuretic. If a person gets mannitol, mannitol's essentially just serves as a solute. It essentially increases urine formation elimination. But it doesn't work as a receptor. It simply is an additional solute. It's a physical chemical property. There's not a mannitol receptor anywhere. It works within the confines of the kidney function, and the kidney's trying to maintain salt and water balance. It essentially is a diuretic because the kidney wants to get rid of that excess solute and more water comes with it. But there's not a receptor. The vast majority of the drugs that we're going to talk about in pharmacy are really going to be receptor-ligand interactions. And as I said, of that, probably half of those will be G-protein coupled receptor kind of things. I think that's where we are. This is the glossary we tried to talk about. If the first discussion was, hey dude, where can I put my drugs? That is, what's the physiology? This is sort of, hey dude, how do my drugs work? And on Monday we'll do dose-response relationships. We sort of touched on that a little bit, so I'm comfortable that in an hour and a half we'll finish the handout and we won't have to work at a super pace. Are there any? We have a couple minutes, I think. Any questions? Let's see if we have a couple minutes. No, we have more than a couple minutes. Any questions that we haven't answered? Yeah.
For this slide, the one that's
yeah.
So are you adding agonists and antagonists?
Let me go back to the slide and I'll answer your question. Yeah. This one. This one right here. Okay. So the question was, on this slide, am I adding agonists and antagonists both? Let me just make this very clear, because you'll see a slide like this probably on an exam. The y-axis is the effect produced by the drug. The x-axis, and the drug here, I mean the effect produced by the agonist. And the x-axis is the dose of the agonist. So the agonist is always being given. In the blue line, it's the agonist only, increasing dose of the agonist. In the red line, it's increasing dose of the agonist, but always in the presence of a little bit of the antagonist.
So you have,
So-
a higher dose of agonist when you increase the dose of antagonist?
When you increase the dose of a competitive antagonist, it increases the dose of the agonist required to produce the half maximal response, the ED50 if you will, and that results in a shift to the right in that dose response curve. But with a fully competitive antagonist, you should be able to surmount that antagonism, and even with a competitive antagonist, you can still get the maximum effect if you push the dose high enough of the agonist. Does that make sense? Other questions? All right, I guess we're done. Thank you.